Hi, Dr. Huckabee here. This is a lecture from last semester on Chapter 6, specifically on entropy and Gibbs free energy. So here is your to-do list. Your to-do list for this lecture is to do your homework assignment, which is due Friday at midnight, to read Chapter 6 and work Chapter 6 problems. As always, please contact me if you're having any issues with the course or if you have any questions. Thanks.
Right, so I kind of mentioned the word earlier, and then I kind of skirted around it. We're going to talk about, we just mentioned enthalpy and mentioned how to find it, but we also are going to talk about entropy. And entropy is a lot more important because the second law of thermodynamics deals with entropy. And if you remember what it says something like the universe is constantly seeking disorder or something like that, right? And that gives you this idea of like somebody's very dirty room and you have to expend a lot of energy in order to clean it and bring order to the system, and that's like the second law of thermodynamics, right? Well, it turns out that in high school and Gen Chem, this is fine. You can talk about the entropy this way because it's like observably correct, but it's not mathematically correct. Maybe the more mathematically correct way to think about it is in this video. We'll let this play so you can get the full effect. So you see at the very beginning, all the nails are super disordered. They can have a ton of different orientations. They can be stacked on each other in lots of different ways. They are at their like minimal energy because they are at their maximum disorder. When you pick up the bin and you start to shake it, now you're exerting energy over the nails and you're causing them to go into a higher energy state. And then because you're overcoming the barrier to causing order, again, saying order, you're allowing the nails to fall into a more ordered state. Your book uses an idea of probability. It says, you know, throw some large number of coins in the air. When they fall to the ground, they're going to have some random distribution of the most probably the most statistically probable set of heads and tails. And that's because that is the highest, it's the highest probability, and there's the most freedom, and you can say order. It's the least ordered way to talk to arrange all of those coins. But really, the nails the nails example is better because you can't put the nails in a specific way like this, where they're all lined up really well, unless you put energy in. Because if you throw them on the floor, they want to just be in some random orientation. And that's really what we're talking about with entropy. Things are going to go into the most, I'm just going to use it, the most disordered way, the way that they are impacting, touching the most stuff, unless you put energy into them. And for the rest of organic chemistry, we're going to be talking a lot about entropy and how that matters in terms of what that's going to mean for the rest of a reaction. And enthalpy and entropy together are called thermodynamics, which maybe you remember from Gen Chem, maybe not, it's okay. But essentially, the point is that entropy is a lot more than just chaos. It is chaos, but there's a lot of math behind it that really gives it a lot more power. So, I don't know, for the rest of the semester, we won't do the math, and we'll just talk about order and disorder and if something is favored entropically. But if you are interested, you could look up entropy and just see how many different ways it affects our lives, how many different chemical phenomena it affects our lives in. A really good one, a really good way that it affects our lives is like with cats. Because a cat sleeping is going to be able to get in a whole lot less trouble than a cat that's up and able to knock off your solo cups off of your entertainment system or something. And it's a really silly example, but it gives a good, it's also an illustrative one because chemicals are the same way. If you have some small molecule or some random cyclic molecule, like this poorly drawn cyclohexane. Let's try it again. There we go. You have cyclohexane. This is going to have a smaller entropy value than the open chain would. 1, 2, 3, 4, 5, 6. Good for me. Because the open chain one is more or less a lot more floppy. It can go around. It can knock stuff off of people's entertainment systems. You know, it can be silly cats. Whereas the cyclohexane is a lot more constrained. It can only really, you know, be a chair or a boat and only affect things a certain amount. Another kind of weird way that entropy matters is whenever you're talking about reactions that go from two things to one thing. So if you have A plus B goes to C, you're now taking two molecules and you're putting them together, and that actually has a big entropy penalty because there are less ways for those molecules to exist in solution. If you have two molecules, you know, they can bump around with each other, bump around with solvent. They can have a lot of energy displaced that way. But now if they're only one, now it's just one molecule floating around and bumping into stuff in solvent. So it really is a force that we're going to talk about as we go through the class. And now is the moment when we do a lot of fun math. No, I'm kidding. It's a moment where I give you a very small amount of math to get to a very important equation that we're going to use in this class. So if you think about the total entropy of a system, you can essentially think about it as the, yeah, I'll do it this way, as the combination of, again, the delta S for the system plus the delta S of the surroundings. Just like enthalpy, the overall enthalpy is the system plus the surroundings. The same goes for entropy. However, because of the second law of thermodynamics, entropy must always be positive for a reaction to occur. Because the second law says it has to be so. So if you have a reaction where entropy is overall negative, the total surroundings and system, it won't happen. That's just a fundamental law of the universe. It will not happen. And so if we're going to find out, like we do with enthalpy, how, if a reaction will occur entropically, how are we going to do that? Well, one way is instead of having two things go to one, if we have A bonded to B, and it goes to A plus B, now we've gone from two things, or from one thing to two. That is a huge increase in entropy, because now essentially we've doubled how much stuff is in solution, and the universe is very happy with that. More molecules equals basically more disorder. It equals more ways for those molecules to exist. Entropy increases, the universe is happy. And just like we had the tables for the bond dissociation energies, which represented the enthalpy, there are also tables for the entropy of different molecules. And you can look those up, and we can do the same exact type of exercise if we wanted to. So, I don't know, I guess we could just say, yay, delta S system, we got it. However, how do you measure the entropy of your surroundings? Or, again, if we were to talk about setting this box of Kleenexes on fire, and we did that, we could measure the enthalpy, but how do we measure the surroundings and their entropy? Who knows what the level of order is in this room? Or is that even big enough? Do we have to observe the planet? Do we have to observe, like, the universe to really know what the entropy is. So we don't have a good way to know what these things are because we don't know what the limits are for what you need to observe. Luckily for us, some very smart people came up with a way to think about the entropy of the surroundings. And you do have to think about these in terms of constant temperature and pressure, but it's not a big deal. We'll just say that's what's happening. And it turns out, through some serious math, that the delta S of surroundings is actually equal to the negative delta H of your system over temperature, as long as temperature and pressure are constant. So this means we can actually know what the delta S of surroundings are because we can measure both the enthalpy of system and of temperature. And through a lot of derivation that I'm not going to do, let's just say magic happens and we get a really, really, really nice equation called the Gibbs free energy equation. This equation is great because you can know the free energy of any reaction system you're talking about, and you can know the entropy of the surroundings. We'll just say delta S surroundings, as well as delta S of your system. And the Gibbs free energy equation is so versatile, you'll actually see it written in literature paper, in chemistry literature papers even today. Just the straight delta G equals delta H minus T delta S. It is very powerful, and it really rules our whole universe. It's cool. But what this also will tell us now is whether a reaction actually will occur or not. Because since we're dealing with both the entropy of the surroundings and system, we are now able to tell if entropy is going to increase for a reaction, which means we should know if a reaction will occur or not. And it turns out that as long as delta G is negative, a reaction will be spontaneous. It means entropy will be positive, which means that the reaction will occur. So the only thing you have to remember is that a negative delta G results in a spontaneous reaction. That is your big, like, star this in your notebook thing. Negative delta G means the reaction will happen. Positive delta G, no reaction. There are special terms for this. We call them exergonic and endogonic. They're super old terms that some physical chemists still use today, but we won't focus on that. Just remember, negative delta G equals spontaneous. And so what you'll see is some plot where you have energy increasing, going up, and a reaction proceeding to the right. And you'll have reactants at some free energy, and the reaction will happen. And as long as the free energy of the products is below that of your reactants, the reaction will be spontaneous. The reaction will happen. So that's thermodynamics in a very general sense. Will a reaction occur or not? But that assumes that, for instance, if you have A plus B going to C plus D, that you get 100% C plus D. But in reality, that doesn't always happen. Just like in acid-base chemistry, we already know that you have to think about reactions in terms of their equilibria and their equilibria constants. Because do you remember when we were talking about this in Chapter 3, we called this Ka, right? The acid dissociation constant. And we use it to measure pKa's, and then we're talking about pHs and how strong acids and bases were. And we had a really good time, and everybody was happy. Yeah, it was a good party. Now we're going to think about equilibria in terms of the overall equilibrium constant. And we're going to change this name. It's going to have an alias of KEQ. And the KEQ is going to let us think about any reaction because we can measure the concentration of the products and the concentration of the reactants and immediately get this KEQ formula. And you might be saying, why are we talking about this right now? We already had this in chapter 3. This is a review. This is stupid. But I'll raise you your rude comment, and I will give you another beautiful equation that's even better, because these things we can directly measure in solution and don't have to know anything else about our reaction. If we measure these in solution and call these these concentrations just KEQ, we can actually find the Gibbs free energy just by multiplying the natural log of KEQ times the universal gas constant and the temperature we ran the reaction at. So now we can know if a reaction will occur just based on, well, it's based on an observation, which is the KEQ, which also tells us if a reaction, if the equilibrium is going well in the reaction. But we can already get the Gibbs free energy for any reaction using real experimental properties, which doesn't sound like a lot to you because we're all sitting in a classroom right now listening to it or listening about this. But whenever you are in a lab and you're trying to figure out real hard information, having data points that you don't have to calculate based on some theory is super valuable and very important, because theory works and is important. Math is always constant, right? However, being able to show yourself that the math works in a laboratory and understand new systems that maybe haven't been thought of yet, that is how you do that with the Gibbs free energy here. You can take any reaction and find the Gibbs free energy of it as long as you know the concentrations of the material or of the compounds in solution.